In this video, we'll see a local correction algorithm for Reed-Muller codes. Recall the definition of Reed-Muller codes from a previous video. Before, we just defined them over F2, but now we're going to define them over any field. The M-variate Reed-Muller code of degree R over Fq is defined as Rm sub q with parameters m, r, and this is equal to the set of all vectors of evaluations of low-degree multivariate polynomials. That is, let's let alpha 1 up through alpha q to the m be all of the vectors in fq to the m. It doesn't matter what order they're in, just fix some order. Then we're going to look at all m-variate polynomials over fq with total degree at most r. And we're going to evaluate those polynomials on all of the points. Each such polynomial is going to give us a code word in our code. So this is just like a Reed-Solomon code, except now it's multivariate. Let's make a few quick remarks. First, as we just mentioned, Reed-Muller codes generalize Reed-Solomon codes. Reed-Solomon codes are just the univariate version. In more detail, the Reed-Muller code over fq with 1 variables of degree r is the same as the Reed-Solomon code over fq with block length n that is equal to q and dimension k that is equal to r plus 1. Another remark is that the Reed-Muller code over f2 in m variables of degree 1 is very similar to the Hadamard code that we saw in the previous video. The difference is that the Hadamard code looked at linear polynomials with no constant term, whereas this Reed-Muller code allows itself a constant term. But that's the only difference. So this definition generalizes two things that we have seen before. In this video, we will see that Reed-Muller codes are locally correctable codes. Let's see the basic idea. So here's the basic idea for bivariate Reed-Muller codes, that is, when m is equal to 2. In this case, we can view each code word kind of as a square. Each point on the square represents an evaluation point, so think of this as being fq cross fq. And each point is an evaluation point alpha comma beta. So the value that goes in the alpha beta position in this square is f of alpha beta for some low-degree bivariate polynomial f. With this picture in mind, let's see how we would locally correct this Reed-Muller code. Suppose we want to recover f of alpha beta, where f is a low-degree polynomial. In particular, f looks like this. It's the sum over all I and j, so that I plus j is at most r, of some coefficient fij times x1 to the I times x2 to the j. And we want to figure out what is this position of the corresponding code word. However, as before, some adversary has gone through and messed up a p fraction of the points. Maybe they've even messed up the point that we're after. We don't know. So now we want to recover this point, given query access to this corrupted code word. To do this, let's consider any line that goes through this point. Maybe it looks like this. Here I've drawn this line as kind of wrapping around this square because we're over a finite field. Formally, we can parameterize such a line like this. That is, we can parameterize it as L of z, which is equal to alpha plus sigma times z for some sigma in fq, comma beta plus tau times z for some other tau in fq. Then if we go in and plug in all of the possible z's, we will get all of the possible points on some line. Here, sigma and tau are giving us the slope of the line. And we can observe that if we plug in z equals 0, we're just going to get alpha beta. So indeed, this line does go through alpha beta. Now, let's consider the restriction of this bivariate polynomial f to this line. By that, I mean, let's consider f of L of z. So we're just going to plug in points that live on this line for the variables in f. And if we plug this into our generic form for f up here, that's going to look something like this. Now this might look pretty nasty, but the main point here is that whatever this polynomial is, this is some univariate polynomial in Z, and moreover, it has degree at most R. That is, it is equal to h of z for some univariate polynomial h of degree at most r. Now imagine that we were to query all of the points along this line. If we ignore these errors for a moment, the points that we query would be evaluation points of some low-degree univariate polynomial. With the occasional corruptions, this is going to be evaluation points of something that is close to some low-degree univariate polynomial. This problem should sound pretty familiar. This is basically just decoding a Reed-Solomon code. We're given corrupted points of some low-degree univariate polynomial, and we want to figure out what is that polynomial. So that's the basic idea for locally correcting Reed-Muller codes. That is, we're going to query the corrupted code word along some line, in particular a random line, and then we're going to use a Reed-Solomon decoder to correct any errors that we happen to hit. So here is our local correction algorithm for the bivariate Reed-Muller code of degree r over fq. As input, we're going to get query access to a corrupted code word, and we're going to get a point alpha beta that we want to query. In more detail, we'll have query access to some function g from fq squared to fq, so that g agrees a lot with some low-degree polynomial. So there's some polynomial f of degree at most r, and g agrees with f in at least a 1 minus p fraction of the places. Another way to say that is that if we were to choose a random evaluation point, the probability that f would not agree with g on that evaluation point is at most p. Then we're given our point alpha beta that we want to query, and what we're supposed to output is a guess for f of alpha beta, and we want to be correct with decent probability. So given that input and output, here's the algorithm. First, we're going to choose a random line through the point alpha beta. To do that, we're going to choose sigma comma tau in fq squared, other than 0, 0, uniformly at random. This is basically picking a uniformly random slope. Then we're going to consider the line L of z, just as before, which is sigma z plus alpha, comma tau z plus beta. And observe that if we plug in z equals 0, this indeed does give us alpha comma beta, so it goes through the point alpha beta. Then we're going to query g at all of the points on the line. So we're going to query g of L of little z for all little z in fq. That will allow us to recover some function h twiddle of z, which is just equal to g of L of z. Now, as we discussed on the previous slide, we hope that h twiddle of z is a lightly corrupted low-degree polynomial. So we're going to use a Reed-Solomon decoder to find some low-degree polynomial h, which has degree at most r, so that the Hamming distance between h and h twiddle, aka the number of points on which h and h twiddle take on different values, is strictly less than q minus r divided by 2. Notice that this value here is half of the distance of the Reed-Solomon code with length q and dimension r plus 1. And so if such an h exists, our Reed-Solomon decoder, for example the Welch-Berlekamp algorithm, will be able to do this. Then what we're going to do is return h of 0. The reason for that is that if we succeeded, and there wasn't too much corruption along this line, then h of z will be equal to f of L of z, and that means that h of 0 is f of L of 0, but L of 0 is alpha beta, so that will just be f of alpha beta, which is what we wanted to return. Okay, so that's the algorithm. What's the probability that it succeeds? Notice that it's not guaranteed to succeed. If we get unlucky and we choose a line that happens to have a lot of errors on it, then this Reed-Solomon decoder will fail. So we need to do some analysis. So I claim that for any p greater than 0, the probability that this algorithm succeeds is at least 1 minus 2 times pq plus 1 divided by q minus r minus 1. We'll come back to this expression in a moment and try to make some sense of it. But for now, let's try to prove this claim. First, let's think about when our algorithm succeeds. The algorithm succeeds as long as there are at most the floor of q minus r divided by 2 errors on the line L of z. That's because the degree of f of L of z is at most r, as we discussed before, and this is the floor of the distance minus 1 divided by 2 for the Reed-Solomon code, which has degree r, and that's the number of errors that we can correct using a Reed-Solomon decoder. So let's try to figure out the probability that this successful outcome occurs. First, let's compute the expected number of errors on a line. So in expectation, the number of errors on the line L is at most 1. That's the one that comes from the point alpha beta itself, which the adversary might know to corrupt, plus the sum over all z not equal to 0 of the probability that g of L of z is not equal to f of L of z. Here I just used linearity of expectation to write the number of errors as the sum over all points on the line of the indicator random variable, which is 1 if there is an error on that point. So we might definitely have an error in alpha beta, and then for all the other points, it's this. Here, this probability is over the choice of L. Since L is random, that means that for any z not equal to 0, this point, L of z, is also uniformly random in fq squared. Therefore, the probability that this occurs is at most p. So the expected number of errors on L is at most this. Then we can use Markov's inequality to get some bound on the probability that there are too many errors on that line. In particular, the probability that the number of errors on L is strictly greater than the floor of q minus r divided by 2 is at most the expectation divided by this, which, adding some plus minus 1s for slack to help us with that floor, is at most 2 times pq plus 1 divided by q minus r minus 1. And that's exactly what we claimed up here. So that proves the claim. Check. All right, I'm going to erase the proof of the claim so that I can write a corollary. The corollary is that for all p greater than 0, the Reed-Muller code with 2 variables and degree r equal to q over 2 over fq, which is a code with alphabet fq and block length n, here n is equal to q squared, is a locally correctable code with query complexity q equal to the square root of n, error parameter p, and failure probability gamma, which is approximately 4p as n gets large. I think I wrote p and q in the opposite order. Sorry about that. Let's quickly see why this corollary is true. Proof. Okay, so the query complexity, that's just the number of points on a line, because in the previous algorithm we queried just a line. And that's little q, the size of the field. Since the block length n is equal to q squared, this is the square root of n as claimed. How about this failure probability? Well, the failure probability is at most this thing, which is 2 times pq plus 1 divided by q minus r minus 1, but r we've chosen to be q over 2. So this is just q over 2 minus 1 in the denominator. And as q gets large, this approaches 4 times p. So here we think of q as growing, since q is the square root of n and n is growing. So as n gets large, gamma, the failure probability, approaches 4 times p. And that proves the corollary. Let's notice also that the rate of this code is constant, as opposed to exponentially small like it was with the Hadamard code. In particular, I claim that the rate is about 1/8. To see why, let's notice that the dimension is the number of monomials x1 to the a, x2 to the b, so that a plus b is at most q/2. How many such monomials are there? That is, how many pairs a and b are there so that a plus b is at most q/2? Well, there are q/2 plus 2 choose 2 such things. And if you work this out, this is approximately q²/8 as q gets large. On the other hand, the block length of this code is q². So that means that the rate is the dimension divided by the block length, which is about 1/8. So this is great. This says that a bivariate Reed-Muller code is already a non-trivial locally correctable code with constant rate. It has query complexity root n. Okay, that's not as small as 2, like when we saw in the previous video, but it is little o of n. It can handle a small constant fraction of errors with some small failure probability, and it has constant rate, 1/8. Moreover, this idea that we saw, this algorithm, doesn't just work for bivariate Reed-Muller codes. As you can imagine, it works for any number of variables. We can just choose a random line in fq to the m and do exactly the same thing. And when we do that, this is what we get. So here's a big table. Let's step through it. If we want a locally correctable code with query complexity q, noise parameter p, which is some small constant, and failure probability gamma, which is some other small constant. Here I just made these small constants up, they're completely arbitrary. And we want it to have dimension k and block length n. Here's what we can get. If we want query complexity 2, we've already seen this, we can do this with the Hadamard code and block length n that is exponential in k. Notice that the Hadamard code, as we remarked before, is very similar to the Reed-Muller code with m variables of degree 1. The other result that we just saw on the other end of the spectrum is that if we want query complexity something like the square root of n, then we can get that with much less blowup in the block length relative to the dimension. So here the block length just has to be like 8 times the dimension or something, much better than 2 to the dimension. And we saw that we can get that with a bivariate Reed-Muller code of degree q/2. For these two intermediate results, we can get these by basically just doing this idea with different values of m and r. In particular, in order to get query complexity log n, we can get away with only a polynomial blowup in the block length over the dimension, and we can do that by choosing m, the number of variables, to be roughly q divided by log q. If we want query complexity a little bit bigger, but not as large as the square root of n, let's say n to the 0.1 or n to the 0.001 or something like that, then we can do that with n on the order of k, some constant times k, where that constant is going to get bigger and bigger as this constant here gets smaller and smaller. And we can do that by choosing m to be some constant. I will leave it as a fun exercise for you to verify that you indeed get these results when you instantiate Reed-Muller codes the right way. Cool. So this table is basically saying that we can get non-trivial locally correctable codes in a variety of parameter regimes by using Reed-Muller codes or Reed-Muller-like codes. You might be wondering if we can do better than this. As previously noted, for q=2, in fact, we cannot. We have to have n basically exponential in k. For q=3, actually, we do have better constructions of locally decodable codes, although, to the best of my knowledge, not locally correctable codes. For q=log n, in this parameter regime, actually, Reed-Muller codes are the best construction we know of locally correctable codes with query complexity big O of log n. It's a very interesting open question if one can do better. For this parameter regime, so the query complexity is some polynomial in n, in fact, it is known that one can do better. That is, we can get rate nearly 1, so we can have n equal to k times 1 plus epsilon for some tiny epsilon, and still get away with query complexity q that is like n to the point 1, or n to the point 001, or n to the point 0000001, and so on. You can check out the lecture notes for more on one way to do this. It turns out that you can do it by just generalizing Reed-Muller codes in the right way. But for now, let's declare success with this. We now have non-trivial LCCs in a variety of parameter regimes based on this really nice simple construction where we look at random lines in Reed-Muller codes.